I will figure that out. Sorry about that. Okay. All right. Okay. So this is that, and let's see what I have for this. Okay. So yeah, we haven't. Yeah, this part I haven't got through, so this is definitely worth recording. Okay. So okay. So earlier, remember I was saying that let's not worry about py because it's given. We just don't know what it is. And then I convince you saying that, okay, don't worry about it, and it's gonna be a beta posterior in the end. But now I want you to all just take out your notebook and try to derive, because you can actually do it, and you'll be able to see that in the end, it is a beta distribution. Okay, so what do we have? If you have a prior to be a beta, and I tell you what this is just from previous slides, okay? This is the density and the likelihood for theta, which is the like the data model. I know it's the binomial. I want you to try to derive the posterior. It's gonna take a little bit, but let's just stop, like pause over here so you can start doing some kind of calculus over here to make sure that you know how to manipulate the terms, as well as in the end, how to see that it is indeed a binomial, indeed a beta distribution. So I will walk around. So I give you the first few, maybe like one more line over here, because this seems daunting, the ones over here. But from there, you can cancel terms. You can actually do things about it. And probably you found this very familiar because from question 3 from the homework, it's a lot of like back and forth doing this. But this is in a more specific context, looking at beta and binomial, while question 3 in the homework is just very generic. I know the joint, I know the conditional, et cetera, et cetera. So what about over here? So here, notice that we're not doing any of the proportional sign anymore. Everything is equal, so you cannot throw away constant, and you cannot, yeah, mostly not throw away constant, but you can cancel terms still. So the first line is trying to just use the Bayes theorem, and the last part of the first line is just trying to write out what the marginal density of y should be if I try to integrate out theta. And the second line, I just did the first step for you, and I would like you to try the rest. If you start canceling terms, especially like the gamma functions over here, that is good. But of course, and the choose function as well. But you probably notice that at some point in the bottom, you have an integral that you have to get rid of. right? So a hint, if you get there already, I'll just try to write the hint over here. So look at this part. Okay. So I put it over here, and not just for fun, saying that it's a proper integral, that it's a proper density that's going to integrate to 1. More importantly, you should realize that if you have a beta distribution, if the density is this, then the integral of p theta d theta is 1, right? Because this, I'm just putting like p theta, that's the density, into it. So it's a proper density. So if I integrate, so this is what, this is p theta, okay? So this is integrating over theta. So if integral p theta d theta is 1, that means this is true, right? This whole term is true. So the hint I want to give it to you is, if when you later, a few steps later, when you get to an integral with some weird terms over here, you should try to think about how I can utilize that a beta distribution with this density going to integrate to 1. How can I utilize this result? So what does this tell us? That means if I try to get rid of the this gamma functions over here, it's going to be the reversed over here, right? Right? Yeah, so later, after a few steps, like you see that you're going to combine the terms for theta, combine the terms for 1 minus theta, then you're going to be left with something like this, but with different powers over here, right? But you have an integral, so what you're going to do, you can utilize this fact that because integral p theta d theta integrates to 1, I have this result, therefore I have this result. So if we're going to have a different power for theta, different power for 1 minus theta, I'm just going to have different a and b's over here in the gamma function. But I can still produce what the integral is, and that will be the biggest trick for this entire derivation. So let me pause again, and I'll just walk around to see if I can give individual help here and there. So once you have done that, you're going to have a different gamma, like a combination of gamma functions. I shouldn't do that. Different gamma functions over here. And then you should be able to recognize it to be a beta distribution with new A and new B. Okay? So yeah, don't worry, let's spend a few more minutes on this. I'm still trying to record from the shop, but I didn't record. In my mind, I'm thinking about what I'm going to do today. What is the new A? What is the new B? try to bring the rest of the slides that I prepared over here. So this one, I just moved the choose function as well as the gamma functions out from the integral, and then I can cancel them, right? Because they're not dealing with theta at all. And then what I have, yeah, so, right, so the down, like down in the bottom, that ratio of the gamma functions is utilizing the technique that I told you about just now, okay? So in the end, you see that it's theta raised to power of a plus y minus 1. 1 minus theta raised to power of a plus b minus 1 minus y. I think it's a typo. Yeah, sorry. I think here should be n, right? Yeah, sorry about that. I'll correct it. Yeah. And down there, down in the bottom is once you're utilizing this fact, you'll be able to get rid of the integral, but you're left with some constants. And this altogether will tell you it is a beta distribution, okay? And it is a beta distribution. Yeah, just rewrite it a little bit, but based on the rewrite, you'll be able to realize that it's a beta. That's really bad. Sorry, I'm gonna write over here. It's a beta distribution with a plus y as your new a, and n plus b minus y as your new b. Make sense? Yes.
I have a question.
Sure, yeah.
So this might be a dumb question, but is there any difference between saying that it's proportional to a beta distribution and saying that it is a beta distribution? Because could we just ignore the integral on the bottom completely?
Yeah,
and
yeah.
know that it is just a beta distribution?
Yeah, good point. So later, and as well as before, like with the uniform example, I was saying that, yeah, just ignore the constant and ignore the integral, and you'll be fine. You will still arrive at the beta posterior, and it's actually in the same form. But for now, this is just, because I think last year when I taught this, students were not convinced. I cannot, like they said, I don't believe it's a beta, so you should derive it. And I realized, yeah, some people, I mean, especially from the more mathy background, I think they like to see how things are done properly. So that's how I prepare this particular slide. But later, as you can see, we will see that as well with the uniform example as well, that we don't care about the normalizing constant. And you will see that. So first of all, yeah, so per Grant's question over here, if we start to write, let's see, if we start to write proportional over here, right? What does that mean? We don't care about this y, right? And we don't care about all of the rest, pretty much. What are we gonna do? We're doing proportional, right? And what we have is beta, and we can also ignore all of these constants, right? So what we have, we're simply having theta raised to a minus 1, 1 minus theta raised to b minus 1, and the data, I can ignore this as well, because the choose function has nothing to do with theta. So here I have theta raised to y, 1 minus theta raised to n minus y. And now I can use the equation over here. What do I have? A plus y minus 1, right? 1 minus theta, n plus b minus y minus 1. So if I take these two terms together, these three terms together, I know that theta given y gonna be a beta, a plus y, and m plus b minus y, right? So later you see, I mean, this is actually what we will mostly be doing in this class. But I still think at the beginning, especially based on my 1 year experience from last year, it will be nice to see the derivation early on. So hopefully convinced now, let's not worry about normalizing constant. Let's not worry about like the integral or summation for the discrete case, integral for the continuous case. What py is, because it's just a normalizing constant. We should be able to just distribution it should follow based on all of the terms that is related to theta. So anything not related to theta, I can get away, right? So if you look at here, yeah, I can use, I guess, different colors over here. Yeah. So if you look at this over here, the only terms that are related to theta is theta raised to power of a minus 1, right? And 1 minus theta raised to b minus 1. So I don't care about the gamma, right? Yeah. And then that's the contribution for the from the prior. So this is what I have. And the contribution from the likelihood, the choose function doesn't matter anymore because it's not related to theta. It's only theta raised to y and 1 minus theta raised to n minus y. So that's the only two terms I left that I need over here. Okay? And then I can just carry on very easy algebra now. It's theta raised to a plus y minus 1, 1 minus theta raised to this. And then, because I know it's going to be a beta distribution, so by the way, because I know this is what we're going to learn, okay? We're going to learn that beta is a conjugate prior for binomial. But for now, if you see this, recognize that it's a beta with a plus y and n plus b minus y. And that's I think, yeah, for this particular exercise, that's the biggest takeaway for you to remember or for you to practice. Okay, so I agree, like this part might be a little bit tricky, especially how to get rid of this particular integral. Yeah, so make sure that you practice. And as I say, I mean, it's not gonna like occur very often, but still I think it's essential skills that we all need to know if you're doing some probability-based derivation. Okay, all right, yeah, I think we should end today for now because this will just be something a little bit different. So, okay, so on Wednesday we're still gonna meet. I think I'm gonna finish just a few last slides from the lecture, and then I provide a lab that we can all practice doing. So on Wednesday, please bring your laptop to class. And I assume everybody has R installed in our studio, so we should be able to start directly. Okay, all right. I don't, but if you live over there, I can staple for you.
Okay.
I should be able to remember it. Just put it on the top. Yeah.
Perfect. Mm-hmm. Also, I don't know if this is open to you, but I have a recording of just the audio. You want me to send it to you?
Yes, okay.
I'll do. I upload it today. I'll do that. I'll send it to like Denise.
Okay. Thank you so much. Yeah.
So I think that the data is the prior and the posterior distribution.
Okay, so theta for now, like I'm showing like, okay, if you want to choose different A and B's for your beta prior, there's like some selection over here. But yeah, later, like on Wednesday, we can see that. You're gonna start with the beta AB, and you combine with, let's say, the likelihood model over there. And you're gonna arrive at a different beta, but it's still a beta distribution. So that's what we're doing. So you start with beta, you end with beta, but with different.
Okay. So yes, the beta is the prior, but it's also the posterior.
But two different betas, but they're all betas.
Okay.
Just like two different normals, but with different meanings and values.
Okay. Thank you.
Oh yeah, I showed that.